So welcome back to our Python class, and we will talk about the elbow method on how to determine the best way of, well, the optimal number of clusters. It's really, the fundamental problem in clustering, because you don't really know what you're looking for, right? Again, you will also notice in our following lectures, we will see today, we will look at there are many different algorithms. So each different type of algorithm for clustering, right, or methods, if you will, they have good properties and bad properties, basically, right? It won't work. No one size fits all everything, right? So k-means, again, it's the most popular, right? It uses single kind of cool method, basically. Starts somewhere, there's a center, and the centers converge, basically, right? It works most of the time, it works really well, unless if you don't run into curse of dimensionality. If your data is not too sparse and not too highly dimensional, right, it will work very well. You can see it can work, again, unevenly sized blobs, that's fine. Again, incorrect size number of blobs, it will work as well. Again, you know there's 3 blobs, but you supply 2, right? So they're different, again, distortions, but again, you can't have everything. Again, the idea is you explore data where you don't know what you're looking for. This is a tool to help you work with data. So let's do this. We'll need metrics. We will need metrics. Inertia, yeah. We will use inertia, yeah. Right, so first we need metrics, right, and right, so lower the inertia, and we will need metric, right, so create a list of inertia values, inertia, well, that will be okay. We can do it by hand. We can use sk scikit-learn, scikit-learn metrics, to call it the inertia. Okay, right, so right, pairwise distance argument mean, okay, sure, why not? Okay, let's see if that's the correct one. I'm not 100% sure, of course. Again, you can't trust AI, remember that. You trust but verify. Right, so let's import it and let's see it in action. So we will need to calculate this, right? So now we'll test. So we will test k-means with 1, well, 1 is kind of silly, 10 clusters, and calculate the inertia, right? So inertia, okay, into range, of course, you know this, right? K-means, right? K-means fit, inertia append, K-means inertia. So again, so we throw away, so we keep throwing away K-means. So of course, so naturally, so we throw away the labels, keep the inertia, right? So we don't have the model, and we'll end up with the model 10. So we can check, right? And let's see, plot the inertia values. I think it's reading my mind. I said plot, and it actually wants to do plot. Okay, marker all. We'll just mark a quick plot again. We have very little data, and k-means is a fast algorithm, so we can afford to do this type of thing. So we have k-means is fast, k-means is fast, and we have little data. So we can do this, right? Right. We may in real life, not all. Some algorithms might be very slow, and we have a lot of data, which would make this unfeasible. Yeah. All right. But just as k-means. That's why k-means is so popular. Okay, but let's run it and let's see the magic. Yeah. So yeah, we have a nice elbow, right? So the trick is, of course, so elbow method. Well, of course, here the idea is to look at the slope when it starts slowing down. So actually, it's here to say whether it's 3 or 4, actually, right? Then you see it's now it again. So ideally, right? Of course, it happens. Of course, now if you had 140, if we had 140 examples, we would, well, if our cluster size was 149, right? You have a very low inertia. We would have a perfect fit, right? But useless model, right? It would be useless, right? Because everyone would have their own cluster. No, again, by same, also cluster size 1 is similarly useless, right? You hopefully agree, right? So only 2 again, 10 or 20, well, we don't know, right? Of course, depends on your data set. It really depends on your data set. But here, so 3 between 4, if you did not know the data, the 2 to 3 jump is the most significant, right? You can see, again, by, of course, you can measure the momentum, you know, and so on, right? The difference, of course, right? But by just visually, it's easier. Again, it's a little bit of an art, right? So again, if this is data I did not know, I would check 3 and 4 and see what's happened, right? 5, 6, it looks like it gets really boring, right? It just tries to fit stuff, but nothing weird is happening. Of course, I could do more, see if anything weird happens. Maybe some extra characters like a pen happens. So I could do maybe, again, max clusters, you know, max clusters equals 10, right? So I would do it here, right? I would do max clusters, right? There you go, and I would do it here, right? Max clusters, right? You know, here, right? Right? Yeah. Oops, sorry, not like that. Max clusters, right? Now let's change it. I'll do 10 plus 1, so I'll do 20 plus 1, maybe, you know, 20 plus 1. Quickly, right? Let's see if it improved. But no, you see, nothing really changed, right? Again, so here maybe it's less obvious. 3 and 4, right, is the actual where the data. One of those would be a good point to explore for interesting, you know, to take a deeper look. Again, remember, it's not always 3 or 4, right? Maybe you need 7 to make sense, right? So it's a very typical method of checking for optimal size. All right, that is, in a nutshell, we've seen k-means and seen how, again, it jumps as high as you tell it to, right? So you say you want 3 clusters, you'll get 3 clusters. You want 50 clusters, you'll get 50 clusters. And it's up to you to make sense of it, right? So again, in our case, we had very helpful labels already, so we could compare. But of course, that's in a real-time situation. It's not always possible. All right. So in the rest of our today's lecture, we will explore other clustering algorithms, and also we'll work with some other data. All right, thank you, and we will continue in the class.